So we have been having some issues that we discovered in the simulated data with both MIRI and NIRSpec. And so the problem that we're having, and I'll sort of try to summarize it in this slide in the top panel here, if we have a look at it. So this is supposed to be a pure quasar emission spectrum, but as you can see, there's these wiggle patterns that you can see in the shorter and the longer wavelength portion that are caused by the undersampling of the detectors. So, and the undersampling occurs both at the slicer level. So this is both of these are slicer spectrographs, and so the slicer width is 0.1 arc seconds, which is several times bigger than the resolution of JWST at near infrared wavelength. And also that persists onto the detector level. And so essentially, as a function of wavelength, you have varying sampling that introduces these wiggle patterns. So just for reference, this is H alpha here, this is H beta, and here is oxygen 3. And so these are fairly nasty artifacts to deal with in the data. You can see it also in MIRI. So this is the middle panel here. This is the short wavelength of MIRI going from 4.9 to 5.7 microns. And same thing here, but just looking at a different spaxel. And you can see that in these two cases, it's just supposed to be a relatively flat continuum without much features in it. But it's essentially the spectrograph introduces these in the data. So this makes it a little bit difficult to do our fitting analysis. And we've thought about trying to smooth over these features or bin over these features. But at the end of the day, what we really want is we want to subtract out the quasar in each one of these distinct wavelength channels. And so interpolating or binning or any sort of things like that does not seem to produce a good enough subtraction of the quasar. So it is still an issue that we are trying to actively deal with. So because of these issues in the simulations, we have had to switch to essentially using the exposure time calculator. The two previous simulations that I showed, one was done by Patrick Ogle with the NIRSpec simulator, and then the other one was done with MIRI Sim, which we did ourselves. But in both of those cases, just those issues are present. So with the exposure time calculator, we basically did a very similar simulation to the other ones, where we have Redshift 1.5 quasar plus galaxy combination. We have a 100-to-1 ratio between the H alpha broad peak and the H alpha narrow emission line peak. This is in the central spaxel. It's a really high contrast ratio here that we're trying to test. So we're really looking to see if our software works in these extreme contrast ratios between the host galaxy and the quasar. So in terms of a bit more physical or on-sky level, so the quasar is at 16.5 AV magnitude at 1 micron, so that's a fairly bright point source. The simulations are done from 0.98 to 1.8 micron range, and then we're simulating 4 emission lines near H alpha, H beta, and the oxygen 3 doublet. And then we have a single emission line component per line with a width of 200 kilometers per second. For the host galaxy, we're simulating spatially, it looks like a 0.5 by 0.5 arc second sigma Gaussian, and it's centered exactly on the quasar. We add a stellar continuum template to the extended emission, plus the emission lines that are extended at the same level. And then for the host galaxy stellar continuum, the magnitude is 21 at 1 micron. So you can see that there's quite a bit of a difference between the point source magnitude and the extended magnitude from the host galaxy. So if we sum up the data cube spectrally, we can produce a white light image that's shown here. And so you can see that it's dominated by the JWST PSF convolved with NIRSpec PSF. And so you can see that it's primarily dominated by the point source. It's hard to see the extended host galaxy in this one. And so the idea of our software is to use information from this bright central spaxel, extract that spectrum, and then fit it to all these spaxels here and try to see if we can remove the quasar emission and see if we can detect anything that's extended from the host galaxy. This is going to be specific to the NIRSpec instrument. So just for reference, I am in the q3dfit directory, and then I'm just going to the Jupyter Notebook directory, and then the file that I'm opening is this run q3dfit NIRSpec etc example. So I have it loaded up here, and to begin with, it's very, very similar to the previous example. So we're just going to load in a few basic Python libraries. Then the next step is downloading the data. And so we have this helper function that does that. Then the next step here is if this directory here in NIRSpec etc doesn't exist, it'll basically create it. And that's where all the outputs from the fitting routine are going to be saved. So the cell is important, and then we're going to give a name to our galaxy, which is just NIRSpec etc. And the rest of it is just checking if things exist, and if not, then it just creates them. Right, so then we're going to actually download the data, but I already have the data cube downloaded, so it's going to skip this download here. So you can basically play around with our etc simulated data. But I just want to mention at this point that the simulations that were done by Patrick for NIRSpec are available online. So they're all on the Space Telescope website. And so you can go there and check this out under the NIRSpec simulations tab. And I have the link to this website in the PowerPoint presentation that's shared. And so for our case, this IFU simulated mode, faint and bright quasar, there's two data sets in there that you can download and play around with and sort of experience these issues that we've been having in the data and see maybe think about it as well. Because it's very likely that at some level it's going to persist into the real data that's going to come from JWST, and we are actively working on trying to mitigate these problems, but it'll also be interesting to know what others kind of think about these issues. Okay, so just going back to the notebook then. All right, so the data got downloaded. Then the next portion here is dealing with loading the data in. It's a very standard file. We're trying to make it as close as possible to the FITS header that you would expect from JWST, but for example, things like the wavelength, the WMAP extension doesn't exist in the etc simulated data, so we have to basically set it to none here for the data to load. And so it loads in the data cube. It spits out some information about the size of the data cube. So it's essentially 30 by 29 pixels, which is 3 by 3 arc seconds. And then there's 39, 26 wavelength channels. And then here it spits out the wavelength range for the data. Okay, so the next portion is we're setting up the systemic redshift of the gas in the system, which is at 1.489. That's just the redshift. This doesn't really get used very much in the data, but it's still important to set it for the fitting routine for the emission lines. Then the next portion here, it's important that we set that there's the range that we want to fit, but there's also a gap in the data at between 1.4 and 1.47 micron, and this is due to a gap between the two detectors on NIRSpec. And so we have to set this range here. The next portion here is we have to basically specify the location of the QSO template, and if the QSO template doesn't exist, it gets created. Let's run that, and that's what's basically gonna be plotted here. So this is the spectrum in the central spaxel that will be used to fit all the neighboring spaxels. So when the fitting happens, the broad emission line, so for example here is broad H alpha, the peak of it gets masked out. And so it's really the wings of the broad emission line and the quasar continuum that is used as anchors in our fitting procedure. And same thing happens for all the other emission lines in the data. And the idea there is we think most of the extended emission spectrally, right, is going to be near the peak of these emission lines within sort of 500 to 1,000 kilometers per second. And so we don't want to overfit the data and potentially remove any of the extended emission that's coming from the host galaxy. Okay, so that gets created. And then the next portion is dealing with setting up which emission lines we want to fit. So as I mentioned earlier, there's 4 lines that are simulated in the data: H alpha, H beta, and oxygen 3. And then we have to set up the number of components that we want to fit, Gaussian components for each emission line. So in this case, we're just fitting 1 component per line. And then the next portion here is dealing with tying the different emission lines. This is important when you have somewhat low signal to noise data, but you have at least one of the emission lines being relatively bright relative to the other ones. So in this case, we want to tie the redshift and the width of the lines relative to H alpha, but this can also be done relative to oxygen 3. It doesn't necessarily matter, but it is something that most likely we'll all have to consider for relatively faint signal. Okay, so the next portion is we have set up the limits on the dispersion for the gas that we're trying to fit, and this is again intrinsic dispersion. So in this case, it's from 5 to 500 kilometers per second. And then the next portion is we're gonna convolve our model emission line with the line spread function for NIRSpec, and we have that information both for NIRSpec and MIRI. And when you do this convolution, the only thing you have to specify is the grading mode that gets used that's for your data. So in this case, it's G140H. Right. So that convolution happens. And then the next portion is masking of for the continuums. In this case, we just set it 500 kilometers per second. But this is something to play around with, and is going to be specific to the source that you're looking at. And in some cases, you probably want a broader wavelength range that you want to subtract out. It just depends on what your quasar looks like. Okay, so then the next portion is we're going to specify which function that we're going to use for the removal of the quasar emission. So this is in the case just fit QSO host, and we're telling it to subtract out the QSO template to be used for the fit and to subtract out, and then we're also providing order for the polynomials that get fit along with the quasar template. Right. So the next portion is we're going to set up the plotting parameters. So in this case, we just want to plot our 3 emission lines that we are fitting, and it's going to be just in a 3x1 window, and H beta, oxygen 3, and H alpha are the 3 lines. So we're trying to plot and see how well the fit did there. And then we're also going to plot the best fit quasar plus broad emission line fit there as well, and try to see how that got subtracted out. So that's the next portion here that gets dealt with that. So the next portion is actually creating this dictionary here that I don't know why this keeps popping up, but anyways, that essentially creates this dictionary that populates all the important parameters that are going to be used in the fitting procedure. So nothing here needs to be edited. Everything above cell 19 gets edited and then imported into this dictionary here. So then this dictionary does get saved to a .npy file, and so this is so you can run this from the terminal and not without having to modify every single bit here every time. So it's helpful for both debugging and then if you want to run this on various number of spaxels in the terminal, there's that possibility there. Okay, so we're basically importing the two important functions that are used in Q3dfit, which is Q3df and Q3da, which is for the fitting and analysis portion of the software. And then we're going to specify which spaxels we want to fit. So in this case, we're going to fit column 13, row 20. So just to remind you that the data cube is 30 by 30 spaxels. So this is fairly close to the center of the quasar. So we are trying to test here whether we can subtract out the quasar emission close to the brightest portion of the point source. And if you don't specify anything here, if you don't even define the columns and rows here, and in the next portion here you don't actually input those in here, what's going to happen is actually going to fit all the spaxels in the data cube. So that's one way if you want to automatically just fit the entire cube. All right, so we're going to run the Q3D fit here on those two on this one spaxel. And so it's just going to spit some information about the continuum and the mission line fitting, and a lot of this just comes from L1 fit. And all of this gets saved into a text file, and so you don't have to necessarily save this yourself. And so you can go back to this later and inspect how good the fit was and extract the necessary parameters. Okay, so let me just scroll down through that. So the fit completed here, and then the next portion is we're going to do the analysis on it and look at the plots that get created. Okay, so here's the fit to this one spaxel is fairly close to the quasar. So the bottom panel here, you can see the fit to the unresolved quasar continuum and broad emission line. And then the top panel shows the total fit here. This is for H beta, oxygen 3, and H alpha. So the purple here is the best fit to the extended emission lines from the host galaxy. And so this is for H beta, this is for oxygen 3, and this is for H alpha. And you can see that it was successfully able to detect extended emission in this one particular spaxel. So, and then the other plot that gets created is the best fit to the entire quasar continuum, so that's the unresolved portion in that particular spaxel from the PSF. And so you can see it does a pretty good job at doing that fit here. So the red spectrum here, that's from the central spaxel, and then the white is the spaxel that we're fitting to.